Hello everyone. Welcome back to Exploring Quantum Physics. I'm Charles Clark. This week we're going to look at solving some of the practical problems of quantum mechanics using the vehicle of the theory of atomic structure and spectra. We'll start with an overview of optical spectroscopy. It's a subject of great scientific and technological importance. In some sense it's responsible for modern telecommunications infrastructure, the knowledge we have about the properties of the sun and the stars, and it's one that provided really compelling evidence, very deep quantitative evidence for the existence of quantum mechanics. Now, from the course home page, you can get to this section, Additional Materials, and within it you'll find a section called Original Scientific Literature, and we will be using two of the papers here in the homework, Bohr Model of the Atom and the Photoelectric Effect, a paper by Einstein. You'll really need to look at these in order to answer some of the homework questions. I mean, it does not require the reading of the full paper, but I hope you will get some enjoyment out of having read original work by Niels Bohr and Albert Einstein. You're all familiar with the beautiful rainbow, an effect seen when sunlight is scattered in a certain way, and it seems that all the colors that we can perceive are found within the rainbow. Now here's an important tool for spectroscopy. We have white light entering into this prism here, and then you see output a band of colors running from red to blue. This technique, this is basically what you might call a deep multiplexing system. The pure white light comes in, and what comes out is a spread out mixture of colors. And this is the technique used by Isaac Newton to demonstrate that white light of the sun was indeed a mixture of colors, because what he did was to pick off a particular color, let's say the blue, and put it through a second prism to find that no further separation of the color occurred. So from the modern perspective, color is a proxy for the wavelength or the frequency of the light, which are related by this characteristic wave equation. The frequency of a wave motion is equal to its speed divided by its wavelength. Now here's a rather clever demonstration of the inverse action of the separation of light. This is a multiplexing effect where one combines a violet, a green, and a red light by the following way. These are, you can't really see it, these are cylinders of water with a hole poured into it, and when they're illuminated from behind, the laser light is entrained in the stream of water that's falling into a dish. And what you see coming out of the dish is scattered light. It's just a random mixture of the violet, the green, and the red colors. So it looks white. So in other words, this shows that the combination of these three different colors gives apparent white light. Now I use this illustration in part to introduce the three reference lasers that we'll use for discussions during the course. These are three commonly used laser lights that you've seen in practice. For example, the red laser pointer with a wavelength of 650 nanometers is widely used in lectures and presentations, as is the green laser pointer, the diode pumped solid state green laser pointer with a wavelength of 532 nanometers, and then the Blu-ray laser player utilizes a violet laser with a wavelength of 405 nanometers. These spread the range of human vision, as we'll see, and so they provide a good set of basic tools. If you want to remember properties of light, it's nice to have some specific examples. So we'll use these at a number of points in the lectures and the homework. Okay, now we'll just have the first and only inline quiz of this introductory lecture to give you some practice in thinking about the properties of light. So the main message of the inline quiz was that when you combine photons, two photons to produce a third, you add the energies of the two photons to get the energy of the third, so that the light from the green laser pointer is made by combining the energy of two infrared photons. Now the rainbow is a very smooth appearing object, and those colors that you saw dispersed by the prism also seem to form a relatively smooth band. But about almost exactly 200 years ago, Joseph Fraunhofer, looking at the spectrum of sun with high resolution, found that it exhibited a number of rather sharp features of a mysterious type. And here is a modern study of the spectrum of the sun. The rainbow has sort of been spread out here and stretched so that you can see very narrow regions of wavelength where there are dark spots in the structure of the sun. Here are our reference lasers laid out roughly where their wavelengths lie, and this notch here is going to be of great interest to us later on. So when this phenomenon was discovered, it was not understood at all, and there's no physical theory that suggested why the smooth light of the sun should be disrupted by so many apparent imperfections.